So our tagline is Turbo Machinery Design Made Easy. We aim to offer the most user-friendly and most widely used turbo machinery design code in the world that's connected in an unrivaled way to the world of computer-aided engineering. And eventually, turbo machinery optimization will become a reality for every engineer, not just for the experts. So we want to provide that software for people at every level.
A user gets immediately a very reasonable initial design, which can be used directly for prototyping, or you go for a 3D simulation or optimization.
Hey everybody, this is Becca from Empowering Pumps and Equipment. I am here today with Ralph Peter Mueller and Chelsea Hall from CFturbo, and they are going to talk to us about how to design energy efficient, high-speed turbo blowers for the wastewater industry. So Ralph and Chelsea, why don't you introduce yourselves further?
Hi, I'm Chelsea Hall, and I do digital marketing here at CFturbo.
Hi, this is Ralph Mueller. I'm president of CFturbo Incorporated in Brooklyn, New York. I'm one of the co-founders, and yeah, I'm a mechanical engineer.
Perfect, let's get started.
We are CFturbo, and today we are going to be discussing pumping and aeration in wastewater treatment. So first we begin with the preliminary treatment, and second and thirdly, in the wastewater production cycle, we have pumping of wastewater collection and aeration of the oxygen supply. Next is removing sludge, scum, and disinfection. CFturbo's role in pumping is wastewater collection systems rely on the forces of gravity and lift stations to move sewage through the plant. Wastewater often must be pumped to a plant's highest process elevation, or the main lift station. And our software is useful for wastewater and freshwater pump design, as well as engineering and optimization services. In the aeration process, decaying organic matter uses up oxygen, aeration replenishes it, and the return activated sludge is pumped to the front of the aerators to aid in the biological process, as you can see here. CFturbo's role in aeration is our software is used for turbo machinery design and 3D flow simulation. Our engineering services aid in design, simulation, optimization, prototyping, as well as testing. And the turbo machine types that we design that would be applicable here would be multi-stage centrifugal blowers, single-stage geared blowers, and high-speed turbo blowers. And you can see the interface of our software here on the right side. There are a number of aeration blower manufacturers on the market, from Lone Star to Atlas Copco, Howden, Sanitaire. And back to our company, we were founded, the parent company, CFturbo GmbH, was founded in 2008 in Dresden, Germany, and CFturbo Incorporated was created in New York City in 2017. And the three arms of our business are design software. So we offer a turbo machinery design software with workflow automation and customization. Engineering services we offer next with design and simulation, digital design space exploration, as well as optimization. And lastly, we have product development, which is used for mechanical design, rapid prototype development, and testing. We have more than 200 clients globally. Here in the States, in North America, we have Amatec, Gold's Pumps, Asylum, Joby Aviation, and elsewhere we have Bosch, BMW, Samsung, Wilo, etc. Our CFturbo software is used for a number of different industries. Of course, first we have water and wastewater, and next marine, food, appliances, chemical and process, mechanical engineering, IT, aerospace and defense, the automotive industry, HVAC, as well as energy, oil and gas.
So I want to talk about the basic CFturbo design methodology. It starts with an duty point or operating point, or in most cases, it's the best efficiency point of the pump or compressor, given by mass flow rate or volume flow rate, pressure difference or pressure ratio, rotational speed, fluid properties, and the inlet conditions. And with these usually 5 to 7 numbers, we can start our design process. So, and behind CFturbo are fundamental equations, fundamental physical equations, which describe the physical behavior in a turbo machine. And additionally, we have collected numerous empirical correlations, which help us to design efficient and reasonable models from the very beginning. And based on this, we can get 3D models out of CFturbo, 3D geometry models, which can be further applied for 3D CAD, for CFD or FEA analysis. Therefore, it's highly important to have interfaces to all these third-party products in the CFD, FEA, and CAD world. And in this overview, you see here the major players in the turbo machinery world. So we work with any of them, and we build interfaces for smooth, seamless operation. And it's not only the interfacing, it's also the establishing of workflows. So, and now we want to go for a live demo with CFturbo. So we design a turbo blower, and you see here the duty point, 8 kilograms per second, 1.9 bar in total pressure difference, and a rotational speed of 40,000 RPM at ambient air. And yeah, so we go now from these numbers to a 3D CAD file. And I want to show you this next. So what you see here is the CFturbo user interface. On the left side, you see different modules you can select. And for these so-called high-speed turboblowers, we have to use the compressor module. Technically, high-speed turboblowers are compressors, yeah, because we have a compressible fluid. And we use our radial mixed flow compressor module for this. And as shown before, we put in the duty point. It's 0.8 kilograms per second. Total pressure difference, 1.9 bar, which is the same as a pressure ratio of 2.9 bar at ambient pressure, and we use 40,000 RPM. If someone wants to compress other things than air, we have here a fluids property database for any kinds of gases and fluids or mixtures. And we have different gas models, from perfect gas model over Redlich-Kwong and Pang-Robinson, which is used for high pressure compressors as well. And we see here the inlet conditions. It's 1 bar at 20 degrees Celsius. its ambient conditions. And on the right side, we have a sketch with a typical impeller type, what we see. So this is what we see specific speed is 31 in European notation, and it's a normal radial impeller. So and from here we can store. This was our global setup. We say OK, and we choose the radial mixed flow impeller option, what we have here. And at first we calculate the main dimension. And usually these type of impellers are unshrouded impellers, so they have no shroud. And we have to define a tip clearance of the blade. And I make this a little bit smaller, 0.5 millimeters. So we have to define if you want to use splitter blades. This is also very usual for these type of compressors. And we have different impeller types available here. We use the standard one. If someone wants to build multi-stage machine, he can configure that here. But that's for the moment. On the right side, you always see some informational values about the design stage. So now it comes to parameter section, and here's really behind the empirical knowledge, the intelligence of CFturbo. Yeah, for example, we just look here at the, let's say, the impeller diameter, and this is calculated according to these empirical correlations which I talked before. So as well, we need an efficiency estimation, similar functions, and this is all from textbooks, from research papers, or from our own data. And that's it for the input. And now we see the main dimensions window. So we have to specify a shaft diameter. There's a proposal. We can make this a bit bigger, and then we calculate the main dimensions, which would be the suction diameter. And I just use here straight numbers and impeller diameter and the outlet width of the impeller. So this will be adjusted. On the right side, again, we have these, the most important thermodynamic values on the inlet and the outlet of the impeller. Again, the meridional contour, a sketch of the Cordier diagram, which gives us the position about of our machine in a recommended range, and the velocity triangles. So, and this was the first design step, main dimensions. And now we can go to the second one. Yeah, just to see here, we have a possibility to go also fully automatic through, but I want to lead you through all the single design steps. So, and the second one would be a meridional contour design. And in this one, take this off first. We see a sketch of the meridional contour. Flow comes from the left, goes to the up, right? And here we see in blue the hub contour, in green the shroud contour, and also the leading edges of the main and of the splitter blade. And this is what I want to adjust at first, right? So I make here straight lines out of it to give a different position. So we have a chance to modify the axial extension of the impeller, and also not only graphically, we can also set exact points. And here you see the modification of the Bezier curves by adjusting the Bezier points to get a nice shaped area distribution in the impeller. Area distribution is computed by area circles, what you may see here. So this is our initial approach for the meridional contour. We also can add now hub and shroud solids. So a hub design, and this is a flexible possibility to create a a curved contour of the hub structure, again by inserting Bezier splines. So it's increased the number, so we can make a certain shape, and this can be directly later computed in an FEA program. So the secondary flow path is not needed yet. And if you're happy with this, we go for the next one, which is our blade properties window, which we use to define or to compute the blade angles on the leading and on the trailing edge. So for this, we have to define the number of blades. So here, because it must be even numbers, because we use splitter blades, that's why we can I add this here I change from 18 to 16. Number of spans, in this case, 5 spans, I would go down to 3, which would be enough in our case. Here in this window, we see we have the option to go for a certain blade shape. This could be from freeform 3D over ruled surfaces until to simpler blade shapes. And for this type of compressors, because in most cases they are manufactured on milling machines, we use the ruled surface option. And then we also have to add a certain thickness, and I changed it here, give a bit higher thickness on the hub for structural reasons. And then on the shroud, we have the option to change our flow rate, if you do it shockless or not, and we have a slip factor correlation according to Wiesner or other scientists. So we use here the Ongio-Wiesner correlation, which is very common for compressors. And then we have here our first idea about the blade angles. On the right side, the blade the velocity triangles, and besides this, again, all numerical numbers, the meridional sketch, and also a diagram about the slip factor correlation. So this was design step number 3. So we have now defined the main dimensions. We have a meridional contour. We know the blade angles on the leading and on the trailing edge to do the work. Now the next step would be how to get from the leading to the trailing edge, and we use the mean-line design window. So, and for mean-line design, we see here on the left the blade after a conformal mapping. So we see here the true blade angles. What I do now here, I modify the wrap angle of the blade. This could be also done numerically here on the right side. And we can have different diagrams to see, let's say, the Mach number or the static pressure or the blade loading. So this gives us a certain first indication about our initial design, and we can also change the curvature of the blade itself, right? So that's about the mean-line design. And next step would be blade profiling. So for this kind, very often we use constant thickness, but CFturbo is also capable in modifying these profiles even to freeform or to read in given profile distributions. Okay, and the final design step would be just to configure the leading and the trailing edge design. This could be simple, elliptic. We could use Beziers, symmetric or non-symmetric, and also a linear option. So I would go here for this Bezier with a higher ratio, and the trailing edge is usually blunt. And that's it for our impeller design. And now we can watch it see it in 3D, how it looks in 3 dimensions. And we can do a so-called model finishing, which gives us the possibility to see a real structural solid for export. And I have added fillets to the model. So what we could do here is also changing the colors, changing the translucency. Right. So we have here an initial design of our impeller. So before I go ahead, I save it. And go for the next component. In our case, so we add now a radial diffuser, and we call this here an add new stator. And we use the radial diffuser option, which is also very usual for this kind of machines. And we can define the inlet and the outlet, right? So the inlet width ratio, I would go for 100%. So we keep the width and could be also a bit shorter. The gap between the impeller and the diffuser. And finally, we define the outlet diameter. I make this also a bit smaller, a bit more compact. So we have a 140 millimeters here. And then I click it and finalize the discharge diffuser. And we see it in 3D. Change our model again. And you see here in silver the impeller and gray is the diffuser. Next step would be the volute. And we just use the standard settings. Next design step would be the type of the cross sections, and CFturbo has various cross sections from rectangular, trapezoidal, round asymmetric. For example, this one here, even with square on top. Or others, and we go back to round for this. And next design step would be the spiral itself. And there's a possibility to use design systems according to Flyder or Stepanov, which is very usual. We can change here our swirl exponent, or we even could do an own and manual progression. For example, we put in here an extension and we set the progression and area ratios or angle ratios distribution, for example. So it's very flexible in the design. And now we only have to do the discharge diffuser. We can define the length, for example. Just make this a bit longer. And the diameter. And to finalize the model, we just do the cut water. It could be done by a simple type or a fillet. So a certain fillet of a certain size. So we close this and see our model in 3D. And that's it. So, and there are only few steps to prepare a CFD simulation model. So we just give him a certain length for an extension so that our boundary conditions are not too close to the computational domain. Right, so on the inside. So then we close the gap between the impeller and the radial diffuser. This will be done here on the impeller side, the setup. Yeah, we make a connection or SI connection, which closes it simply. And the final step would be for our computational model adding an inlet pipe at a stator and give a certain length, let's say 100 millimeters or so, again for the same reason that our boundary conditions are not too close to the compressor stage itself. So we go to 0, and here it's 55. And we finish the model. And we do this to create a hub nose for these compressors. And the hub nose, this is an adjustment here on this side. We do this in the meridional contour, split the curve, right? You split the curve and make a Bezier out of it with a certain length, certain angle. And we close this model, make this a straight line. So this is okay. And now our model is basically ready for export and simulation. And we just add here the hub color, and we have a computational model. So again, I save it and export the file. And this is the export panel of CFturbo. We see here a lot of neutral file formats. IGES, Parasolid, then all the CAD files for the usual CAD software, and then the CFD codes. So we choose the components, and here on this in this example, I just want to show you how it works. We have to choose a directory where the simulation runs or where the export goes to, and we can also prepare settings for Simerics, for example, which is the solver I choose here. And we could do some STL quality definition. We can do some mesh refinements already for the impeller and for the volute, which could be also local adjusted. And we can make solver settings. That means steady state or transient, the number of iterations. So it usually for these type of compressors would be a bit higher than 500, maybe 1,500 iterations. And we recommend then a second order upwind method to run it. And if we say okay, we can just export the model. So, and the model export would take about 2 minutes and another 2 minutes for the meshing, and then we would be ready for a simulation. Yes, and with this, I would go for the next part of the presentation and show the results. So this is what we have seen right now. We have in the live demo, we have created a single stage centrifugal compressor for this duty point. And now I want to talk about the results we got and for the further development on this machine. So what I explained, we have exported the model to Simerics MP and to run a simulation for the given design point, for the duty point at 40,000 RPM. And so the pressure rise would be the result. And what we have, so we will see later in diagrams what the results will be. The computational time here was less than 1 hour per operating point on a modern i9 processor notebook with 8 cores. And here we see the performance map for these compressor. In yellow, it's the 40,000 RPM, orange 30,000, in gray 50,000. So this is the typical range. And the efficiency, this here is the total stage efficiency, and we can reach about 80% in peak efficiency for these typical design range between 0.6 and 0.9 kilograms per second. So this is what we talked about, simulation of single design point. Very often it's not enough. We want to also optimize our models. And for this, in this case, we have set up an optimization workflow combining CFturbo with Simerics and Heats. So Heats is an commercial optimizing tool, well known, and also very user-friendly. And we applied this model for Simerics and Heats. So how do you do this? It's really pretty simple steps. We make a setup of CFturbo and Simerics within Heats as the first step. Second step would be we select independent optimization parameters, and for this case, we just choose 8 independent parameters, and there will be also some dependent parameters then. So we have to define our optimization target. In this case, it was just the peak efficiency, to raise the peak efficiency and to reach a certain pressure difference and to run the simulation. And then it's just a matter of your computational resources and your computational power. And as I said, we just run these optimization on a notebook, on a modern notebook with 8 cores. And so it took about 4.5 days for these 130 designs what we investigated. And out of these 53 designs which reached our target, so we choose our best one. So this, in our case, it was the design called design number 81, so which has some different parameters, as you can see. And the results can be seen here for this single design point. Yeah, we raised the pressure, the total pressure by 8% and the efficiency by 2.5%. So this is the status of the moment for this project, and usually you should run, and we recommend to do this transient flow simulation for selected design points to be sure before you create your model, and of course you usually do an FEA analysis before you build a prototype. And if you're interested in this, we welcome you to register for a free trial at cfturbo.com. Thank you very much.
Thank you, Chelsea and Ralph. That was a great presentation. So right now I have a few questions for you. The first one being, what is the position of CFturbo on the CAE software market?
Sure. CFturbo is a highly specialized niche product for turbo machinery design exploration. So it has applications in many different industries, as we talked about earlier. And from the beginning, the water and wastewater industry has been one of the key drivers in our software development strategy.
Awesome. So really being wastewater being a key driver, what specific applications does CFturbo software cover for the wastewater industry?
Specifically, we can design a number of different different products with our software. So we have axial, mixed flow and radial pumps, including inducers, impellers, diffusers, return channels, and volutes, as well as multi-stage centrifugal blowers and single-stage turbo blowers and compressors.
That's a lot. So compared to other conceptual design codes, what are the essential features of CFturbo?
Yeah, I take this. essential is, first of all, it's a very user-friendly software, and it's not only for experts, it's also for beginners and young engineers. And so the thing is, you can use it for various industries and small companies and large corporations. So it's a very, very widely used is possible, right? So this is one thing, and then the second thing for CFturbo is that a user gets immediately a very reasonable initial design, which can be used directly for prototyping, or you go for a 3D simulation or optimization. So this is I think the second important point. And I think the third thing of our advantages, I would say, it's the number and also the quality of the interfaces for the CAD and FEA systems, and for to set up optimization workflows with various third parties software packages, not only one. So that's it.
Awesome. So this is pretty applicable leading up to TPS. What simulation methods should be used to design turbo machinery components?
Yeah, really, when we talk about the turbo machinery components itself, like impellers, stators, or complete stages, we definitely have to use 3D models, right? And the 1D correlations, or the 1D models, loss model based correlations, or simplified models like potential flow, or other simplified models like through flow, are not really helpful for a 3D geometry optimization. So in the end, you should go from an excellent starting geometry to a 3D modeling, and all in between. The 1D stuff might be helpful for system simulation, but not for optimizing turbo machinery components.
And I think that's very important to note. All right, Chelsea, Ralph, thank you so much for your time. Of course, if anyone has any questions for Ralph and Chelsea, definitely reach out to them. If you want to get information about the free trial, definitely go to CFturbo.com. And of course, if you have any questions that we can relay to them, feel free to reach out. Thank you.
Thanks.
Thanks, Becca. Thanks, bye.